Have you ever found yourself staring at a technical article, especially, in the world of machine learning, and just thinking, "Ugh, I wish I could just understand this deeply without feeling completely lost?"
Oh, absolutely.
Like
Yeah,
that familiar feeling of being totally overwhelmed by complex concepts, isn't it?
absolutely. And that's precisely our mission with this deep dive. We're here to pull back the curtain on some of the most powerful machine learning algorithms. Our goal is to simplify them so dramatically that even if you're a total beginner, you can grasp their core concepts, truly understand their purpose, and see exactly how they're used in the real world.
Right.
Think of us as your guides, making the complex, simple, actionable, and, well, genuinely understandable for you.
And to help us do that, we've been diving deep into an incredible resource, Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow by Aurélien Geron.
Great book.
This book is practically a legend in the machine learning community, and for good reason. As many on Reddit have rightly highlighted, it strikes that perfect balance between essential theory and practical real-world implementation.
It really does.
It's incredibly project-driven, uses real data sets, and the writing style is just so clear and approachable, making even really complex ideas accessible. We've gone through this book, along with some related errata and study sheets, and we're here to extract and share the most important nuggets of wisdom so you don't have to sift through it all.
Yeah, cut through the noise a bit.
Machine learning can often feel a bit like magic, this complex black box that just does amazing things.
For sure.
But honestly, it's not magic, and we're here to show you exactly how these powerful algorithms work, one clear explanation at a time. So get ready for some genuine aha moments as we shed light on these fascinating tools.
Okay, so to frame our discussion today, it's really important to remember that these algorithms, as powerful as they are, don't just exist in isolation.
Right, they're part of something bigger.
Exactly. They're always part of a larger, carefully structured machine learning project from start to finish. To give you a concrete example, imagine a real estate company.
Okay.
Their core business problem might be to build a reliable model capable of predicting the median housing price in any given district, based on other available metrics like the district's population, its median income, or maybe the average number of rooms per household. Understanding this kind of tangible problem helps us see exactly where each algorithm we're discussing fits into the bigger picture.
So, if our mission is to predict a specific numerical value, like a house price, what kind of machine learning task are we actually engaged in? Are we classifying things, or is it something else entirely? Because I know those terms can get a bit confusing for someone just starting out.
That's a fundamental distinction, and you've hit on a crucial point. When we have labeled data, meaning we already know the actual housing prices for our training example,
Okay, labeled data. Got it.
right? And our ultimate goal is to predict a continuous numerical value. We are performing what's called a supervised learning task.
Supervised, like having the answers to learn from.
Exactly. It's supervised because the model learns from examples where the right answers, the labels are provided. And more specifically, because we're predicting a continuous number, not a category, it's categorized as a regression task.
Regression for numbers. Okay.
Now, if the client's need were different, say, they only wanted to know if a house was affordable, medium priced, or expensive.
Ah, like categories instead.
Precisely. That would transform it from a regression problem into a classification problem. In that case, we wouldn't need a precise numerical output. Rather, we'd focus on assigning it to a specific category.
Okay, so we're focused on predicting numbers with regression. But how do we actually know if our predictions are any good? What's the ultimate scorecard for a regression model telling us if it's hitting the mark?
Right, good question. For regression tasks, the go-to performance measure you'll hear about most often is the root mean square error, or RMSE.
RMSE. Sounds a bit technical.
It sounds technical, but it's quite intuitive, actually. RMSE essentially measures the typical distance or average error between the values our model predicts and the actual true values. So if our model predicts a house price of $500,000 and the actual price was $510,000, that's an error of $10,000.
Okay.
RMSE takes all these individual errors, squares them, that gets rid of negative signs, and really emphasizes the bigger mistakes, averages them, and then takes the square root to bring it back to the original scale, like dollars.
So a lower RMSE is better, closer to the real price.
Exactly. A lower RMSE means our predictions are, on average, closer to reality, which is exactly what we want. Clearly defining these performance measures up front is absolutely crucial for any successful project. Because if you don't know how you're measuring success, how do you know if you've found it?
Makes sense. So with RMSE as our critical measure of model quality, the big picture here is that we're not just training an isolated model and calling it a day. We're aiming to build a full, robust system.
The whole pipeline.
That journey goes from acquiring and meticulously preparing the raw data all the way through to launching our model into the real world and then continuously monitoring and maintaining it. Understanding these individual algorithms, like the ones we're about to dive into, is absolutely crucial because they are the foundational building blocks for that entire practical application, guiding every step of the process.
Well put. They're the engine inside the car.
All right, let's unpack this. Have you ever heard the old saying, two heads are better than one?
Sure.
Well, in machine learning, sometimes hundreds of heads are better. That concept brings us directly to our first core algorithm, random forest.
That's a fantastic way to put it, because random forest is an incredibly powerful concept known as an ensemble method.
Ensemble, like a musical group.
Kind of. It means using a group of models together. Think of it this way. Instead of relying on a single, potentially complex and brittle decision tree to make a prediction, a random forest builds many, sometimes even hundreds or thousands, of individual decision trees.
Wow, okay. Lots of trees.
Yeah, lots of little trees. And each of these little trees is trained on a slightly different random subset of your original data and also a random subset of the features or attributes of that data. So they all get a slightly different perspective.
Huh. Okay, so they don't all see the exact same thing.
Right. When it's time to make a final prediction, the random forest doesn't just pick one tree's answer. Instead, it collects the votes from all of these individual trees or averages their numerical predictions in regression to arrive at a highly robust prediction. This combining of many simpler, often weaker, models the individual trees into one robust, strong model, the forest, is a truly elegant way to push machine learning algorithms forward.
Clever.
What's particularly significant here is that this collective averaged approach dramatically reduces a common problem called overfitting.
Overfitting, that's when it learns the training data too well, right? Including the noise.
Exactly. A single, very deep decision tree might learn the training data too perfectly, including all its noise, and then fail miserably on new, unseen data. The random forest, by averaging, cancels out those individual trees' overspecializations, making the final model much more reliable.
I can really visualize that. It's like assembling a highly diverse jury. Instead of relying on one single judge to make a highly complex decision all on their own, you have many jurors. Each juror might hear slightly different parts of the case, or perhaps focus on different aspects of the evidence presented. Then they all deliberate and collectively decide.
Yeah.
This collaborative approach almost always leads to a much more robust and fair verdict than if you just relied on one potentially biased or overconfident individual.
Yeah.
It's that wisdom of crowds effect truly amplified.
Exactly. Perfect analogy. In our ongoing example of predicting housing prices, a random forest regressor would operate by creating thousands of these miniature rule sets, which are our decision trees. Each of these tiny trees might focus on different aspects of a property, perhaps some on income levels in the district, others on the number of rooms, and still others on specific geographic locations or age of the property. By combining their individual predictions through that averaging process, the random forest can arrive at a highly accurate and surprisingly robust final price prediction for a given house or district.
Makes sense.
It's precisely because it aggregates so many diverse perspectives that it tends to perform exceptionally well and generalize beautifully to new data.
So the big idea with random forest is that it's a superpowered team approach to prediction. It leverages the collective wisdom of many individual models to dramatically boost accuracy and prevent overspecialization, making the overall prediction far more reliable than any single model could achieve on its own.
You've got it. Teamwork makes the dream work for models.
Following on that team idea, what if your team isn't just voting independently, but actively learning from each other's mistakes?
Yeah, now you're talking about boosting.
That's where boosting algorithms, and specifically gradient boosting, come into play, right?
That's a fantastic distinction because boosting is another ensemble technique, just like random forest. But its approach is fundamentally different and often even more powerful. Instead of building independent models simultaneously, boosting builds them sequentially.
Sequentially. Okay, one after the other.
Exactly. What happens is the first model makes its predictions. Then the subsequent models in the sequence don't just try to predict the outcome from scratch. They specifically focus on correcting the errors that the previous models made.
Oh, interesting. So it pays attention to what went wrong.
Precisely.
Mm.
It's an iterative refinement process. where each new model is essentially a learner that pays more attention to the data points that the prior models struggled with or got wrong. Gradient boosting is a particularly popular and powerful form of this, known for its extremely high performance and accuracy, especially with regression tasks like our housing price prediction. It essentially allows models to learn from their own deficiencies, progressively building a stronger and stronger predictor with each step. It's like a persistent student who keeps practicing the hardest problems.
I can totally visualize that. It's like imagining a student trying to solve a really tricky math problem. They take a first stab and they might make a mistake.
Hmm.
Their teacher doesn't just give them the answer. Instead, the teacher points out that specific error, perhaps highlighting why it was wrong. Then the student tries again, focusing intently on improving that one area.
Yeah.
This iterative process, where you're constantly learning from and refining based on your past errors, is exactly how boosting algorithms work. They're always striving to be better by pinpointing and fixing what went wrong before.
You'll find boosting algorithms, particularly gradient boosting, used widely in incredibly high-stakes practical scenarios. For instance, beyond our housing price example, they are staples in financial modeling.
Like stocks.
Exactly. Imagine predicting complex stock price movements, or trying to identify which customers are most likely to churn, meaning they might cancel their service. A boosting model would be excellent here because it can identify subtle patterns that even earlier, simpler models missed, incrementally improving predictions over time by repeatedly focusing on the hardest to predict cases. As mentioned in the errata, gradient boosting performs great with regression tasks, which makes it directly applicable to predicting continuous values like house prices with very high precision and robustness.
So the core idea behind boosting is that models learn from their own past mistakes, literally, creating a powerful sequence of incremental improvements. This iterative refinement allows them to achieve remarkably accurate and robust results, tackling even the trickiest prediction challenges by building intelligence error by error.
Spot on. It's sequential learning and error correction. Very powerful.
Now, what if you're not trying to predict a number, like a house price, but rather a category, like yes or no, whether an email is spam or not spam, or classifying an image as cat or dog?
Good question.
This is where logistic regression steps in. And despite its name, it's a fundamental and incredibly useful player in classification.
Indeed, the name logistic regression can be a bit misleading because it's overwhelmingly used for classification tasks, not for predicting continuous numbers.
Right. Not really regression, then.
Not in the usual sense.
Yeah.
Its main purpose is to estimate the probability of an instance belonging to a particular class. So, for example, it doesn't just say this is spam, it's more nuanced, saying there's an 85% probability that this email is spam.
Okay, so it gives a confidence score, too.
Exactly. It accomplishes this by finding what's called a linear decision boundary. Think of this as the best possible straight line, or a flat plane, that effectively separates different categories of data points in your feature space. Even with some messy data or outliers, it's quite robust and can converge to a reasonably good solution.
A straight line to divide the groups.
Basically, yes. To calculate these probabilities, it typically employs a special kind of mathematical squashing function, often called the sigmoid activation function, which takes any input value and transforms it into a smooth probability between 0 and 1.
Sigmoid. Squashing it between 0 and 1.
Yep. And to measure how well its probability guesses align with the true labels for two-class problems, it uses something called binary cross-entropy loss. Don't get hung up on the technical names. The key is it's figuring out how wrong its probability guesses are and then adjusting to get closer to the right answer.
That makes perfect sense. I like to think of it like drawing a clear line in the sand. If you're sifting through emails and deciding whether one is spam or not spam, logistic regression tries to find the absolute best possible straight line to divide the characteristics of typical spam emails from those of non-spam ones. Any email falling on one side of that line is classified as spam, and anything on the other side is not. It's all about creating that crisp separation and knowing how confident it is about that decision.
Exactly. You'll find logistic regression incredibly widely applied in real-world scenarios due to its simplicity and interpretability.
Interpretability, meaning you can understand why it made a decision.
Yes, often you can look at the model's learned weights and see which features were most important for its decision. It's less of a black box than some other methods. For instance, it's commonly used in classifying customer reviews as either positive or negative, or in predicting whether a loan applicant is likely to default based on their financial history.
Okay.
In our housing example, if the real estate company decided they didn't need an exact price, but rather just needed to quickly categorize a house as affordable, medium, or expensive, effectively transforming our regression problem into a classification, one with three categories. Logistic regression would be a strong candidate. Its efficiency, speed, and that interpretability make it a go-to model for many binary classification tasks and a great starting point for multi-class problems.
So, the core takeaway for logistic regression is that it's your reliable workhorse for drawing a clear dividing line to predict which category something belongs to, all while estimating the probability of that classification. It's straightforward, robust, and incredibly versatile for making binary decisions.
Nailed it. Simple, effective classification.
Now, if logistic regression draws a line, then the support vector machine, or SVM, takes it to the next level. It tries to draw the best possible line with the widest possible margin.
Ooh, good one.
It's like a strategic master of optimal separation.
That's a truly insightful way to describe it. Support vector machines are indeed incredibly powerful and versatile algorithms, capable of handling both classification and regression tasks with great precision. For classification, the core idea is exactly what you described, to find what's called the optimal hyperplane.
Hyperplane sounds fancy, just means the best boundary line or surface.
Exactly.
Yeah.
Don't let the fancy name intimidate you. A hyperplane is simply the best possible decision boundary, whether it's a simple line in 2 dimensions or a higher dimensional flat surface that maximizes the margin between the different classes.
Maximizes the margin, like the empty space between the groups.
Precisely. It creates the largest possible buffer zone, or street, between the closest data points of each class. These closest points are called the support vectors, hence the name. Support vectors.
This approach is often called soft margin classification because it intelligently allows for some errors or outliers within that margin, making the model more robust to noisy data. It doesn't insist on perfect separation if it means making the margin too narrow.
So it can handle a bit of messiness.
Right. But what's truly fascinating here, and a major reason for SVM's power, is that they can also handle incredibly complex, non-linear classification problems.
Nonlinear. So when a straight line just won't cut it? Exactly. When the data is all tangled up, how do they do that? They use a clever mathematical trick called kernels, like the polynomial kernel or the popular Gaussian RBF kernel. These kernels work by implicitly transforming your data into a much higher dimensional space where, suddenly, a linear boundary can effectively separate even the most tangled data.
Whoa, okay, so it lifts the data into a higher dimension to make it separable.
You can think of it that way, yeah. It's like looking at the problem from a completely different, higher vantage point to find a simpler solution without actually calculating those high-dimensional coordinates, which is the clever part.
That's really neat.
And you can also fine-tune SVMs using hyperparameters like C, which controls the trade-off between having a wide margin and minimizing classification errors.
So how strict it is about misclassifications versus margin width.
Right. And gamma for RBF kernels, which acts as a regularization hyperparameter, influencing how much influence a single training example has on the decision boundary. Think of them as crucial dials you can turn to get the best performance.
I love this analogy. Imagine you have 2 different colored marbles scattered across a table, and they're a bit mixed up, maybe even overlapping.
Yeah.
And SVM is like trying to put a divider between them, but it doesn't just put any divider. It meticulously places the divider in a way that gives the most space on both sides to the marbles closest to the line for each color. It's maximizing that breathing room.
Nice visualization.
Now, if the marbles are really tangled and you can't even draw a straight line to separate them, an SVM using kernels is like magically lifting them into the air into a higher dimension where they naturally spread out until you can finally slide a flat sheet, that hyperplane, perfectly between them. It completely changes your perspective to find that optimal separation.
That captures the essence perfectly. This strategic power makes SVMs highly effective in a truly wide variety of realistic use cases. They're extensively used in image recognition, for instance, in tasks like classifying handwritten digits, or in text categorization, where they might distinguish between different types of documents based on their content. The SVR, or support vector regressor version, can be directly applied to our housing price prediction scenario. and its performance can be greatly optimized by carefully tuning its kernel, C, and gamma hyperparameters.
So it does regression too.
Yep. The flexibility to handle both linear and complex nonlinear data, combined with their strong theoretical foundation and ability to generalize well, makes SVMs a go-to algorithm for many challenging problems where precise separation is key.
So the profound insight with SVMs is that they're like master strategists capable of finding the widest, most effective separation line, even when data seems hopelessly tangled. They achieve this by cleverly reshaping their perspective, finding clarity where others see chaos, leading to remarkably robust boundaries.
Well said. Maximum margin classifiers with some clever tricks up their sleeve.
So far, we've talked about predicting values or categories when we already have examples with known answers that supervise learning.
Right.
But what if you have a huge pile of data and absolutely no labels, no predefined categories, and you just want to find natural groupings within it?
Now we're venturing into unsupervised learning. This is where the data itself has to tell us its structure.
Exactly.
And k-means clustering is one of the most popular and intuitive algorithms in this category. The fundamental idea behind k-means is to group data points into a predefined number of k distinct clusters.
Okay, K is the number of clusters you want. You have to tell it that up front.
Yes, that's a key parameter you set. It works through an iterative, almost dance-like process. First, you tell it how many clusters you want, that's your k, and it initializes k central points called centroids. Could be random starting points or smarter ones.
Centroids, like the centers of the clusters.
Exactly. Then, it repeatedly performs two steps.
Mhm.
It assigns each data point to the closest centroid based on distance.
Okay, find your nearest center.
Then, after all points are assigned, it recalculates the centroids based on the new average position of the points now assigned to each cluster. So the centers move.
The centers adjust to the points that join their group.
Precisely. This process of assigning and recalculating continues until the cluster assignments no longer change significantly, meaning the clusters have stabilized. The overall goal is to minimize inertia.
Inertia.
Yeah, inertia is simply the sum of the squared distances between each instance and its closest centroid. What this measures conceptually is how tight and well-formed your clusters are.
Yeah.
Low inertia means tighter clusters, points are closer to their centers.
So you want low inertia, tight clusters.
Generally, yes. To improve the chances of finding good clusters, k-means often uses a smart initialization method called k-means++ to pick better starting centroids, rather than just random ones, which can prevent it from getting stuck in a suboptimal grouping. This helps uncover hidden patterns or underlying structures in otherwise unlabeled data.
That makes so much sense. I think of it like a kindergarten teacher with a huge box of unorganized Legos.
Okay, I like this.
The teacher isn't told what colors they are or what shapes, but wants to sort them into, say, 3 piles, so K equals 3, based purely on their natural characteristics. K-means is like the teacher repeatedly grabbing a handful of Legos for each pile, then adjusting where the exact center of each pile is based on the average characteristics of the Legos now in it.
Mm-hmm.
This continues until each Lego is neatly in the pile with the closest average characteristics, and all the piles are as tight and homogeneous as possible. No one told the teacher the categories, but natural groupings emerged.
That's a perfect everyday analogy. Captures the iterative nature really well. In practical applications, k-means is widely used for tasks like customer segmentation.
Grouping similar customers together.
Exactly. Grouping customers by their purchasing behavior, demographics, or engagement patterns to tailor marketing strategies more effectively. It's also used for document clustering, to organize similar articles or news reports without prior labels.
Okay.
In our housing example, while predicting prices is a regression task, k-means could be a valuable pre-processing step. For instance, after visualizing the geographic data, you might notice distinct high-density areas or regions with strikingly similar property characteristics. K-means could precisely detect the main clusters in that geographic data, allowing you to then treat those clusters as new, incredibly useful features for your price prediction model, giving it more context. Like belongs to cluster 1 could be a new feature.
Okay. So clustering can actually help supervised learning too.
Absolutely.
Yeah,
Feature
okay.
engineering through clustering is quite common.
So the key insight with k-means is that it's your essential tool for uncovering hidden natural groupings in data when you don't have any predefined categories or labels. It essentially allows the data to tell you its own story, revealing structure you might never have found otherwise.
Spot on. Finding structure in the unlabeled wilderness.
Did you know that sometimes having too much information can actually be a bad thing for a machine learning model?
Oh yeah. Definitely.
It's often referred to as the curse of dimensionality.
Yeah.
And that brings us to principal component analysis, or PCA.
It's absolutely true. The curse of dimensionality refers to how models struggle and their performance can degrade significantly when dealing with data sets that have an extremely large number of features or dimensions.
So, like thousands of columns in your spreadsheet.
Exactly. More features isn't always better. Sometimes it introduces noise, makes calculations way slower, and makes models prone to overfitting because they can find spurious correlations in all that data. Principal component analysis, or PCA, is a crucial technique designed specifically to combat this. It falls under the umbrella of dimensionality reduction.
Reducing dimensions. Getting rid of features.
Sort of, but in a really smart way.
Hmm.
What PCA does is transform your existing data into a completely new, smaller set of dimensions, which we call principal components. These new axes are strategically chosen to capture the maximum amount of variance, or in simpler terms, the most important information, the most spread, from the original data.
So it finds the directions where the data varies the most.
Precisely. The first principal component captures the most variance, the second captures the most remaining variance while being uncorrelated with the first, and so on. The real beauty of PCA is its ability to preserve as much of the data's variance, its unique spread and patterns as possible, while allowing you to project down to a much smaller number of dimensions, effectively discarding the less important, redundant, or noisy components.
So you keep the important new dimensions and drop the less important ones.
Exactly. This means you can use PCA for powerful data compression without losing the critical information that defines your dataset. It often serves as a powerful pre-processing step, simplifying the data before feeding it into other machine learning models.
That makes so much sense. If I'm thinking about it, imagine you have a very high-resolution photo of a sprawling landscape. It's packed with millions of tiny, tiny details. PCA is like intelligently compressing that photo into a much smaller file. It doesn't just randomly remove pixels. Instead, it meticulously finds the most important aspects, like the main shapes of the mountains, the dominant colors of the sky, or the key textures of the trees, and reduces the file size significantly.
Yeah.
You might lose some of those tiny, imperceptible details, but you absolutely keep the essence of the landscape, making it perfectly recognizable and usable in a much more efficient way.
Exactly. Great analogy.
Yeah.
In practice, PCA is incredibly useful for reducing the number of features in a dataset before training a model. This can dramatically speed up training time as the model has far less data to process for each instance.
Faster training, definitely a plus.
Crucially, it can sometimes even improve the model's performance by effectively removing noise or redundant information that might otherwise confuse the algorithm. For instance, if you were describing a house with thousands of very specific features.
Like every single detail imaginable.
Right. PCA could reduce that to just a few dozen essential components that still capture most of the important information about the house. This makes the subsequent machine learning task much more efficient and effective, allowing models to learn more general patterns.
So the profound insight with PCA is that it simplifies complex, high-dimensional data by extracting only the most important information, transforming an overwhelming torrent of data into a focused beam. This makes models faster and more efficient without sacrificing too much crucial detail, effectively getting to the heart of your data's story.
Couldn't have said it better myself. Finding the essence of the data.
How do we stop a powerful machine learning model from getting too smart for its own good? So smart, in fact, that it only understands our data, the training data, and completely fails on anything new.
The overfitting problem again.
We want it to perform beautifully on new, unseen data, not just ace the practice test.
That's a critical challenge in machine learning, and it's called overfitting. Overfitting happens when a model learns the training data too well, including all its noise and peculiarities, and then consequently performs poorly when presented with new, unseen data. It's like a student who memorizes every single question and answer on a practice exam, but then bombs the actual test because the questions are phrased slightly differently.
Right, doesn't generalize.
Exactly. To combat this, we use techniques called L1 and L2 regularization. These are fundamental tools, especially for models like deep neural networks and linear models, such as ridge regression, which uses L2, and lasso regression, which uses L1.
Ridge and lasso. Okay.
What regularization does is add a penalty to the model's complexity during its training phase. It's a subtle but powerful way to guide the learning process, basically telling the model, hey, try to keep things simple.
Adding a penalty for being too complex.
Essentially, yes. Let's break down these penalties. L2 regularization, also known as ridge regression, as a penalty based on the square of the model's weight values. Think of weights as how much importance the model gives to each feature. This penalty encourages the model to use smaller weights overall, distributing the influence of features more evenly and preventing any single feature from dominating the prediction too much. It makes the model less sensitive to small changes in individual features, smoother, less jumpy.
Okay, L2 shrinks the weights, makes them small.
Right. On the other hand, L1 regularization, or lasso regression, as a penalty based on the absolute value of the weights. The fascinating thing about L1 is that it has a strong tendency to drive some weights to exactly zero.
Zero. So it completely ignores some features.
Exactly. When a weight becomes zero, it effectively means that the corresponding feature is completely ignored by the model, thus performing an automatic feature selection. This can simplify the model and make it much more interpretable, especially when you start with tons of features.
Wow, L1 does feature selection automatically. That's cool.
It is pretty neat.
Yeah.
If you want the best of both worlds, there's also ElasticNet, which intelligently combines both L1 and L2 regularization. It has parameters to control how much of each you apply.
ElasticNet, a mix of both.
Yep. And it's also worth noting that hyperparameters like gamma in SVMs, which we discussed earlier, also act as regularization parameters, controlling how flexible and prone to overfitting the decision boundary is. Regularization is a general concept.
So if I'm trying to wrap my head around this, it's a bit like a coach trying to prevent an athlete from overtraining before a big competition.
Go on.
If an athlete trains too intensely, they might burn out or get injured, performing poorly on game day. The coach, knowing this, imposes certain penalties like reducing training intensity or adding crucial rest days to ensure the athlete doesn't exhaust themselves or overspecialize for practice.
Mhm.
The goal isn't just to be good at practice, but to perform consistently well during the actual competition. Regularization is that smart coach for our models, nudging them towards better, more consistent real-world performance.
Precisely. That's a fantastic analogy. Regularization is a standard and essential practice when training any complex machine learning model, from simple linear regression to the most intricate deep neural networks. Its purpose is to ensure the model generalizes well to new unseen data.
Right.
If, for instance, our housing price model was becoming overly complicated, trying to perfectly fit every tiny fluctuation and outlier in the training data, applying L1 or L2 regularization would force it to learn simpler, more general patterns. This makes the model far more robust and reliable for future price predictions. It prevents it from merely memorizing the training set and instead encouraging it to truly learn the underlying relationships.
So the profound insight with regularization is that it's less about making models smarter and more about making them wiser. It keeps models honest, forcing them to learn generalizable patterns rather than just memorizing noise, ensuring they perform beautifully not just on practice data, but on the real-world challenges that truly matter.
Exactly. Wiser, not just more complex. Promoting generalization.
Now, what if the past holds the crucial key to the future, but it's a really long past, and a regular model simply forgets important details from way back when?
Sequential data with long-term dependencies. A classic challenge.
That's where LSTMs, or long short-term memory networks, step in, especially when it comes to sophisticated forecasting tasks.
That's a perfect setup for LSTMs. They're a specialized and incredibly powerful type of recurrent neural network, or RNN.
RNNs, they handle sequences, right, like text or time series.
Exactly. Regular RNNs are designed to process sequential data where the order matters, like time series, sentences, or audio. The problem is, simpler RNNs struggle significantly to remember information over long periods.
They have short memories.
Pretty much. It's like trying to understand a very long, complex sentence, but by the time you get to the end, you've forgotten the beginning. This is known as the vanishing gradient problem, which leads to difficulty learning long-term dependencies.
Okay, I can see how that would be a problem for, say, stock prediction.
Definitely. LSTMs elegantly solve this through sophisticated internal memory cells and a system of gates, input, forget, and output gates.
Memory cells and gates. Sounds like internal plumbing.
Kind of. These gates are like little regulators. They allow the network to selectively remember information from the past and carry it forward in the memory cell, update its understanding as new data comes in, or forget irrelevant details that are no longer useful.
So it learns what to keep, what to update, and what to throw away.
Exactly. This remarkable ability to maintain context from much earlier in a sequence makes LSTMs incredibly effective for tasks where understanding the historical context, even from the distant past, is absolutely crucial for making accurate future predictions. They effectively learn what information is important to carry forward and what can be safely discarded, allowing for robust, long-range pattern recognition.
That's a fascinating concept. I think of an LSTM like an incredibly advanced, intelligent note-taking system. Instead of just writing down everything it hears, which would quickly become overwhelming and difficult to sift through, an LSTM is like a system that actively decides what information is important to remember, what existing notes need to be updated with new insights, and what can finally be forgotten as new information streams in. This intelligent filtering and retention allows it to recall crucial details from the distant past when it needs to make a new, informed prediction. It's a selective, intelligent memory, constantly evolving.
That's a very accurate way to picture it. Given their unique ability to process sequences and retain long-term dependencies, LSTMs are invaluable for many complex, real-world applications. They're commonly used for tasks like predicting stock prices, where understanding historical trends over many months or years is vital, or for forecasting sales volumes based on past seasonal patterns and market shifts. They're also fundamental in natural language processing for understanding the context within long sentences or entire documents, and for things like income forecasting, as seen in various machine learning study sheets. In our housing example, LSTMs could be used to predict future median house values in a district, not just based on current attributes, but by truly understanding and learning from its deep historical price trends and other time series data, capturing patterns that unfold over extended periods.
So, the key insight with LSTMs is that they are specialized neural networks equipped with a long memory, making them ideally suited for understanding, learning from, and predicting complex patterns in long sequences of data. They are the go-to for tasks where historical context, no matter how far back, is everything.
Precisely. Remembering the important stuff over long stretches of time. Hashtag practical considerations and next steps in ML. Now that we've covered some of these core algorithms, it's absolutely critical to shift our focus to the practical considerations that make these models actually work and work well in the real world.
All right, the algorithms are cool, but how do you actually use them effectively?
Exactly. One of the most important aspects, extensively detailed in the Part 2 source, is data preparation. This is truly the unsung hero of machine learning, often taking up like 80% of a data scientist's time.
80%. Wow, so getting the data right is huge.
It's massive. Before you feed data to any model, you must meticulously clean and prepare it. Garbage in, garbage out, as they say.
I can imagine. If your ingredients are bad, your cake won't be great no matter how good the recipe is. So what are some of those essential preparation steps we need to be aware of?
Okay, great analogy. Think of it as preparing your ingredients. First, you'll often encounter missing values. For example, if some houses in your dataset don't have an average income recorded, you can't just leave those blanks.
What do you do, just delete those houses?
Sometimes, if there are only a few. But often you want to keep the data. A common strategy, especially using scikit-learn's simple imputer, is to fill them with the median value of that feature across the whole dataset.
Median, not the average. Why?
Because the median is more robust to extreme outliers than the mean, the average. Imagine if Bill Gates lived in one district. His income would massively skew the average income for that district, making it a misleading imputation for everyone else. The median, the middle value, is much more stable.
Ah, okay. Less affected by extreme values. Makes sense.
Next, you often have categorical data, like the ocean proximity attribute in our housing dataset, which might describe whether a house is near the ocean or inland. Models typically only understand numbers, so you need to convert these categories.
The words into numbers.
Right. One way is ordinal encoder, which assigns a number to each category, like 0, 1, 2. But that can be problematic if there's no natural order. Is inland somehow less than near ocean? Probably not.
The model might misinterpret that.
Exactly. So a better, more common approach for categories without a natural order is one-hot encoding. This turns each category into a new binary feature, a column of zeros and ones. So near the ocean becomes a 1 in a new is near ocean column and 0 everywhere else for that house.
Okay, so each category gets its own yes-no column.
Precisely. This prevents the model from mistakenly assuming an order that doesn't exist.
Oh, that's a clever way to avoid misleading the model. So what about making new features? Does that come into play here too?
Absolutely. It's a crucial step called feature engineering. Beyond cleaning, creating new, more informative features from your existing ones can significantly boost model performance.
Like combining existing features.
Exactly. For instance, in our housing data, we might derive rooms per household by dividing total rooms by household size. This new feature often has more predictive power than the raw number of rooms or households alone. You can even build custom transformers within scikit-learn to automate these specific feature creations, like a combined attributes adder for our housing example. It keeps things organized.
Custom transformers?
Neat. And finally, a step that's often overlooked but incredibly important is feature scaling. Imagine you have house prices ranging in the hundreds of thousands, but the number of rooms is just between 1 and 10.
Huge difference in scale.
Right. Most machine learning algorithms, especially those that calculate distances between data points like k-means or SVMs, do not perform well when features are on wildly different scales. Features with larger numerical values can unfairly dominate the learning process.
So the big numbers overshadow the small ones.
Pretty much. So you apply methods like min-max scaling, which transforms values to a specific range, often 0 to 1, or standardization, which transforms them to have a 0 mean and unit variance. Standardization is generally preferred for many algorithms, as it doesn't squash outliers into a small range as much.
Okay, scaling makes all features play fair.
That's the idea. These steps handling missing values, encoding categories, feature engineering, scaling are absolutely critical for getting meaningful and accurate results from any model.
Wow, that sounds like a lot of individual steps and transformations to keep track of, especially as your data set gets bigger. Is there an efficient, perhaps automated way to manage all these data preparation stages so you don't get lost in a spaghetti of code? Because that sounds like a headache waiting to happen.
You've hit on a core challenge, and fortunately, scikit-learn offers elegant solutions with its pipeline and column transformer features, which are absolute lifesavers.
Seriously.
Pipelines, like for plumbing.
Huh, sort of. A pipeline allows you to chain multiple transformation steps together in a defined sequence. So you say, first, impute missing values using the median imputer. Second, add these custom attributes. Third, scale the features using standardization.
Okay, defining the whole sequence at once.
Right. The beauty is, once you define this pipeline, you can apply it consistently to both your training data and any new unseen data you want to make predictions on. This prevents inconsistencies, like forgetting a step or applying them in the wrong order.
That sounds much cleaner. What about the column transformer?
The column transformer takes this a step further. It lets you apply different sets of transformations to different columns all within one object.
Oh. So you can say, do this to the number columns and do that to the category columns. Exactly. For example, applying numerical transformations like scaling only to numerical columns and one-hot encoding only to categorical columns all managed together. This ensures consistency, makes your data preparation code much cleaner, more robust, and incredibly easier to manage, even when dealing with diverse data types. It's like building a custom assembly line for your data.
Okay, pipelines and column transformers are definitely tools to remember, game changers for keeping data prep organized.
Absolutely. Now, beyond just preparing the data, accurately evaluating your model is paramount. We saw earlier with the decision tree regressor.
Right, the one that got a perfect score on the training data.
Yeah, getting a 0.0 error on the training data is not a sign of a perfect model. It's a huge red flag indicating overfitting. The model has essentially memorized the training data, including all its noise and peculiarities, and will almost certainly perform poorly when presented with new unseen data.
The student who memorized the practice tests.
Exactly. This is precisely why we rely on robust evaluation techniques like cross-validation, specifically k-fold cross-validation.
K-fold cross-validation. How does that work?
This method rigorously evaluates a model's true performance by splitting your data into several folds or segments, say 5 or 10. The model is then trained and tested multiple times. Each time, a different fold is held out as the test set, and the remaining folds are used for training.
So it trains on part of the data, tests on another part, and rotates which part is tested.
You got it. You end up with multiple performance scores, one from each fold. Averaging these gives you a much more robust and reliable estimate of how well your model will truly generalize to real-world data, giving you a clearer, more unbiased picture of its true capabilities. It's like having your student take several different versions of the test to truly prove their understanding.
Okay, so cross-validation gives a much more trustworthy score than just training and testing once.
Much more trustworthy. Essential for avoiding fooling yourself.
Okay, so once you have your model, you've prepped the data meticulously using pipelines, and you've evaluated it rigorously using cross-validation to ensure it's not just memorizing. How do you then find the absolute best settings for all those different algorithms and their hyperparameters? It seems like there are endless combinations of dials to turn.
You're right. That's where hyperparameter tuning comes in, and it's a crucial step to maximize your model's performance. Remember, hyperparameters are those adjustable dials or settings you choose for the model before it starts learning things like the number of trees in a random forest or the C and gamma values in an SVM.
Right, the settings you give the algorithm.
Manually trying out different settings would be incredibly tedious and inefficient. Imagine trying hundreds of combinations by hand.
Yeah, no thanks.
Fortunately, scikit-learn provides powerful tools to automate this. Grid Search CV allows you to define a grid of hyperparameter values you want to test. For example, for random forest, you might say try 100, 200, or 300 trees and try a max depth of 5, 10, or 15. Grid Search CV will systematically try every single possible combination within that grid, 100 trees depth 5, 100 trees depth 10, etc., evaluating each one using cross-validation to find the best performing set. It's exhaustive, ensuring you find the optimal combination within your defined search space.
Grid search tries everything in the grid. Sounds thorough, but potentially slow.
It can be, especially if your grid is large or the model takes a long time to train. That's when randomized search CV becomes invaluable.
Randomized search, how's that different?
Instead of exhaustively checking every combination, it randomly samples a specified number of combinations from the hyperparameter distributions you define. For example, you might tell it, try 50 random combinations.
Ah, so it explores the possibilities randomly instead of systematically. Exactly. This allows you to explore a much larger hyperparameter landscape far more efficiently, often finding near-optimal configurations in a fraction of the time it would take grid search. It's particularly useful when you have many hyperparameters to tune.
Okay, so grid search is thorough but slow. Randomized search is faster for bigger problems.
Got it.
These tools automate the process of finding the optimal model configuration, saving you immense effort and making sure your model is truly performing at its peak.
So once you've gone through all this data prep, model selection, robust evaluation with cross-validation, and hyperparameter tuning with grid search or randomized search, and you have that perfectly tuned, well-performing model, what's the very next step? How do you move from a successful experiment to a real-world solution that actually helps people or a business?
That's the crucial final stretch, taking your model from development to deployment. The very next practical step is to save your trained model.
Save it, like a file. Yeah, exactly. Tools like joblib.dump in Python are commonly used for this, serializing your model, including the learned weights, parameters, and even the pre-processing pipeline, so it can be loaded later without retraining.
Why save it?
It preserves all the hard work. You don't have to retrain it every single time you want to use it for prediction, or if your development environment shuts down unexpectedly, it captures the final state of your trained artifact.
Okay, saving the model is step one after tuning. Then what?
From there, it's about launching, monitoring, and maintaining your system. This involves several things. Plugging your model into the live input data source, like a web application form or a data stream, running thorough tests in a staging or production environment, and then continuously monitoring its performance in production.
Monitoring, checking if it's still working well over time.
Absolutely. You need to set up alerts if performance drops significantly. This could happen due to changes in the real-world data, maybe customer behavior changes, or economic conditions shift. This is called data drift or model decay.
Ah, the world changes, so the model might become outdated.
Precisely. You also need to monitor the quality of the input data itself, because if you start feeding a model poor quality signals, the model's predictions will inevitably become poor itself. It's also best practice to regularly retrain your models on fresh, new data, maybe weekly or monthly, depending on the application, and to keep snapshots or versions of your model at various points in time. This ensures your system remains accurate, relevant, and robust as the world and the data within it continuously change. It's an ongoing commitment, not a one-off task.
That truly reinforces the idea that machine learning isn't a one-and-done deal. It's an iterative process, a continuous loop of improving and adapting.
The life cycle.
And as you highlighted, sometimes that means needing to update your code because of new library versions or shifts in how things are done. It's all part of the continuous learning journey for anyone working in data science, making it both challenging and incredibly rewarding.
Couldn't agree more. Always learning, always adapting. Hashtag outro.
We've covered a remarkable amount of ground today, haven't we? We started by framing our journey within the machine learning project lifecycle, understanding supervised learning, regression, and the importance of RMSE.
Laid the groundwork.
Then we peeled back the curtain on some truly powerful algorithms. From ensemble methods like random forests and boosting that leveraged collective intelligence, to fundamental classifiers like logistic regression and the versatile support vector machines that find optimal boundaries.
Covered a lot of the core toolkit.
We learned how to uncover hidden patterns in unlabeled data with k-means, simplified complex data with PCA, and kept our models honest and robust with L1 and L2 regularization.
Tackled unsupervised learning and crucial practical techniques.
And we even peered into the future with LSTMs, designed to remember long-term patterns and sequences. It's been quite the tour.
Our overarching goal throughout this deep dive was to give you a clear, actionable starting point, to truly peel back the layers and show that these powerful tools, while mathematically sophisticated, are fundamentally understandable.
Yeah, demystify it a bit.
Exactly. It's not magic. It's a series of logical steps, clever mathematical formulations, and thoughtful, systematic application that you can absolutely grasp.
So as you continue your own learning journey and encounter more of these fascinating topics, consider this. If even the most complex AI systems are built from these foundational pieces, what kind of problems can you begin to solve now that you get it?
Good question to ponder.
What simple, everyday challenge in your life or work could be transformed, perhaps even revolutionized, by applying just one of these powerful algorithms? The possibilities are truly endless.
It starts with understanding these building blocks.
Keep exploring, keep questioning, and keep diving deep into the world of knowledge.